Hey everyone, we are from the team topohack, and our objective was to look over differences between ISAT elevations and elevations from extracted from DEMs over non-flat areas, and also over flat areas. Can we use a snow off DEM and compare it with ISAT collect, which was during snow on condition, and get snow differences from that. Our team developed some functions to download data on the fly to do some unique spatial data analysis. Did some sort of analysis. It's not publishable, obviously, but I hand over to Friedrich, and he'll tell you.
Yes, so I was going to give you guys a quick overview of the GitHub repo we put together and how we organized ourselves. This is the topohack repo. You see we created a contributors folder. That's kind of where we kept our own personal notebooks that we're working on so we don't run into any Git conflicts with each other. Just a strategy one possible strategy to keep in mind. Here, every one of us had our own folder, and it was kind of our safe space to work, because a merge conflict with a IPython notebook is pretty nasty. And we had an images folder. This was just a place to keep images or static plots that you might want to pull into a example notebook, which you might want to share with the group. So if one of us had created something that they wanted to share with the group, maybe someone on the team expressed an objective that they had, and then someone else with more Python experience went in and helped them achieve that objective. We put those notebooks in here. So these are kind of some canned examples. Then we had another folder with scripts. This was just some basic utilities, shell scripts or Python scripts that kind of do some conveniences. Again, where maybe one of us with more programming experience was trying to help someone who maybe didn't know how to write a shell script but needed something to do their science. And then finally, we also created, as Shashank mentioned, the topolib library. Joe will speak about that in a second. Just before we go on to that, here's the README with some more information about the tools we use, high-level goals, and at the bottom, we took advantage of the wiki. So the wiki tab over here has more information about everything we did, our data management strategy for the project, and our daily agenda, kind of what we did every day, as well as on the right here, some of you might be interested, this was our Git workflow for the team that we worked together, and that actually worked quite well. And then also we had a Git workflow for taking part in the tutorials. So if you want to check that out, I think that worked quite well. We all contributed a lot and were able to get it done without any major hiccups working through GitHub. So let me pass it on to Joe to talk about topolib.
Okay, so for the topolib part, so the way we organized it, we created a Python package, and I don't know if you guys are familiar with Python packages, but they're pretty handy. Like we said, if you want to integrate shareable components, the essential piece you need for that is called setup.py. This is how you can identify on Python. You have a folder underneath the repository that is a library. I won't dive into details there, but if you have questions about that, I'm happy to share it in the coffee discussion. But basically what it does, it declares topolib to be something that is available through the Python ecosystem. And the way it kind of roughly works is that you can, in the end, then say from topolib, can you guys read that? I guess not. Let me increase that. From topolib, import ISAT2 data. For instance, that's our download class we created to get stuff downloaded. And this is really nice to have, for instance, across multiple notebooks. You know, you don't need to just copy and paste a bunch of code. And instead, you just say, like a Pythonic way, okay, here's a shared component, and this is how you use it. So with that, I should pass Justin, who has an integrated workflow that uses actually those libraries.
All right, so like Joe said, as we went along, we tried to break these things out into several different components. So instead of pasting between active IPython Jupyter notebooks, we could instead actually use these utilities in an integrated workflow. So this is kind of our attempt at getting at that. I showed an example for Tuolumne Meadows, which is in California. And what we decided to do is add a bunch of dependencies, and then as we went along, actually just create one cell at the beginning where all of our inputs were put. And then we could just run from there on out. So hopefully this is a kind of workflow that you could employ for using our tools for any domain, any time period. So we're looking at where data is stored, where we're going to put it, some raster that we have, whether or not we're restricting our region of interest by that raster. That's an option. If not, we can explicitly define our boundaries. We can explicitly define what variables we want to pull in, whether we're going to use the full period of time over that area, or if we want to define a start date and end date, and then credentials going forward. So with edits in this cell alone, you should be able to just run on going forward with just all of our functions. So for example, using our functions, we could, we did this so we could see what we wanted to pull, but probably should collapse that. So as we went along, we could search the granules that overlapped our area, and then actually use this calling function to actually pull those granules and download them into a data file. With that, we could download all the H5s that correspond to that download, create a dictionary, and then actually subset over our region of interest with our raster. So here's some example flight lines over Tuolumne. And then, we could have the option going forward whether to look at these individually, see how they did in total error compared versus the raster. These are those same points actually plotted with elevation values. So you can see, there's some points that have problems, but others do very well. Break it apart, see what variables were most important for these errors. You could actually take a look at the terrain characteristics. See, for example, if slope was most important in attributing these errors, or maybe aspect or things like that. So essentially, we're kind of just trying to show that, breaking apart into all these different modules is a good way to have a plug and play module where you can essentially just move this sort of analysis to anywhere that you may have validation data.
I'm HP, and I'm a recovering MATLAB addict. So I've been handcuffed to MATLAB since the early 90s. So I'm definitely more of like an end user case here. I wasn't writing very much of this Python, but I adapted it to some of the LiDAR data sets from SnowX and managed to get it running on my laptop locally. So just a quick example of Grand Mesa here. So it's like an 11,000 foot mesa that's pretty flat on top. So wanted to just see how well it did compared to an airborne LiDAR data set there. Once we used the correct date, I started comparing in the middle of the summer where there might have still been some other issues. This is from a more recent airborne acquisition, but the mean bias is on the left there. So sort of like 5 to 30 centimeters was kind of the bias we were seeing in that data set. Here's just an example profile as you're coming off the mesa.
And to wrap it up, a small update from Nepal. So we tried to compare the ISAT track profiles with a worldview HIMAT which is available. This is Max system. Max. So this is where the glaciers lie over that. The color scheme is not very intuitive, and I think you guys might have difficulties in discriminating the ISAT tracks as is, but I wanted to have them share the same color range and things so that maybe just you can compare it visually. And then I calculated so some of the functions which David showed yesterday using ISAT1 data, I tried to compare elevation change for glaciers, and I was surprised that most of the glaciers were gaining elevation there, so that something must be wrong. Then I compared the profiles as is. So this is for one of the tracks separated into 6 different beams. More or less, it looks to be similar, but if we zoom in on the color range and if we calculate the differences here, there are some outliers. Not able to visualize this going down to minus 40 to plus 40. We see that there are some errors, but going forward to minus 10 to plus 10, we can see that there is a large spread. One caveat here is that I have not removed the glaciers from here, so some of those might be coming from the glacier surfaces. But that's one of the conclusions. HP explored it for another topographically rugged terrain, and he also had higher standard deviation than the result which he got for Grand Nisa. So maybe something to look into as we go forward. And all of our team members learn to code in Python. So everyone can write functions in Python.